Here we will see data parallelism architecture. Data parallelism is a form of parallelization that distributes the data across different nodes which operate independently of each other. Each node applies the same operation on its allocated subset of data. This approach is particularly effective when dealing with large data sets where the task can be divided and executed simultaneously, which reduces computational time significantly. The mechanism of data parallelism is as shown. In data parallelism architecture, the dataset is split into smaller and more manageable chunks or partitions. Each partition is processed independently by separate tasks running the same operation. This distribution is done in a way that each task operates on a different core or processor, which enables high-level parallel computation. Advantages of data parallelisms are scalability. Data parallel architecture are designed to handle large volumes of data. As data grows, you can simply add more nodes to the system to maintain performance. Performance. The ability to perform computations in parallel leads to significant speedups, particularly for large data sets and computationally intensive operations. Due to the fact that data does not move around as often to different workers, there can also be a performance gain from less serialization. Simplicity. Since the same operation is applied to each partition, this model is relatively simple to understand and implement. Disadvantages of data parallelisms are communication overhead. The nodes need to communicate with each other to synchronize and aggregate results, which can add overhead particularly for large number of nodes. Limited use cases. Data parallelism works best when the same operation can be applied to all data partitions. It is less suitable for the tasks that require complex interdependencies or shared state across tasks. Best use cases for data parallelisms are batch processing. When there is a large amount of data need to be processed all at once, data parallel architecture is useful. This is a common use case in big data analytics, where massive datasets are processed in batch jobs. Machine learning. Many machine learning algorithms, especially those that involve matrix operations, can be easily parallelized. For instance, in the training phase of neural network, the weights of the neurons are updated based on the error. This operation can be done in parallel for each layer, which makes data parallelism as a great fit. High partitioned input and output. Data parallel framework excels when the input and output are partitioned in such a way that the workers can evenly match the partitions and redistribution of the data is limited. Stream processing. The data parallelism approach is well suited to stream processing where the same operation is happening to the data in real time. Frameworks used for data parallelisms are Apache Spark, which is a notable data parallel framework and is widely used in big data analytics for tasks like ETL, that is extract, transform and load, predictive analytics and data mining. It is particularly known for its ability to perform complex data transformations and aggregations across large datasets. And Bytewax, which is known for its ability to handle large continuous streams of data and do complex transformations on them in real time.